super common question is, how can a photon, which has no mass, have momentum? This equation says that momentum, which is written as p, is equal to an object's mass, written as m, times its velocity, which is written as v. P equals mv. That's the equation. And you immediately see the problem. Well, a photon of light travels at the speed of light, which is written as c, by the way. Its mass is 0. And 0 times a number is 0. So the momentum of a photon should be 0, right? I mean, it's a really good question. Yet physicists are certain that photons have momentum. So let me start with explaining this in terms of equations, then go to a more intuitive explanation, although even that's really not all that intuitive. First, let me remind you of the equations that you would have encountered in any introductory physics class. I already reminded you of the momentum one. There's also another equation that connects mass, velocity, and kinetic energy. This is kinetic energy, which is written as Ke, equals 1/2 times the mass, m, times the velocity, v, squared. So we say that Ke equals 1/2 mv squared. You probably remember all that. Now let me show you how kinetic energy and momentum are related. Let's start with the momentum equation, P equals mv. Now square both sides. You get P squared equals m squared v squared. So far so good, right? Now, divide both sides by m. On the right-hand side, the bottom m cancels one of the top m's, and you get P squared divided by m equals mv squared, which should remind you of something, specifically the kinetic energy equation. You can replace the m times v squared in the kinetic energy equation with this P squared over m thing, and what you find is that the kinetic energy equals the momentum squared divided by twice the mass. Ke equals P squared divided by 2m. Okay, the first conclusion to draw here is that in classical physics, and I remind you that these equations were devised back in Newton's time when they didn't worry about things moving near the speed of light. But even back then, we can see that kinetic energy and momentum are related. We have an equation with energy on one side and momentum on the other. And this kind of means that anything with kinetic energy must also have momentum. Of course, we still have that m kicking around, which is 0 for photons, so I haven't really answered the question. And I didn't intend to at this point. I just wanted to show you that kinetic energy and momentum are related, even classically. Okay, now to get into something you might not have known. Let's move into this new material. And I want to tell you something, and that is that these equations aren't completely true. Of course, like a lot of times when people toss around the word sheeple, what I just said was a little misleading, and the real story is a bit complicated. The real truth is that those equations are special cases that only work for objects with mass that is moving at slow speeds. Now comes the next surprise, and that surprise involves Einstein. Of course, Einstein was all about moving at super fast speeds near the speed of light, so you know that he's going to pop up in any discussion involving photons and momentum. And when you think about Einstein, you almost always think about his famous equation, E equals mc squared. E equals mc squared is also an approximate equation and one that only works for objects with mass that are stationary. It's not a general equation, and it doesn't work for massless objects, nor objects that are moving. So now we're ready to get to the truth. I put the three equations I've mentioned so far here. E equals mc squared, P equals mv, and Ke equals P squared divided by 2m. And all of these equations are just fine and correct, but they are all equations that only describe objects with mass that move slowly. Those equations fail in other situations. It turns out that there is a more general equation that works for all situations, and it looks kind of like Einstein's famous equation. This equation is energy squared equals the momentum times the speed of light squared plus the mass of the object times the speed of light squared, all squared. E squared equals PC squared plus MC squared, all squared. Now this equation works for everything: massive objects, massless objects, things moving near the speed of light, things moving at the speed of light, and things that are stationary. And we can look at the special cases. For instance, let's see how it works in the special case of a photon. Since the photon has 0 mass, this second term on the right-hand side goes to 0. And we have that energy equals momentum times the speed of light. So here we see that energy and momentum are equal, except for a constant. And if an object isn't moving, then its momentum is zero, which means that p is zero, which gets you back to Einstein's equation, E equals mc squared. So I guess the first lesson is that when you learn an equation, it's super important to understand if it's a special case or not, and if it's a special case, when it applies and when it doesn't. The bottom line is that the familiar equation, P equals mv, just doesn't apply for massless photons, and the question of photon momentum, well, completely sensible, arises from using the equation in a situation where it was never intended to be. By the way, let me tantalize you a bit. That 1/2 mv squared thing is itself only an approximation for kinetic energy that works only at very low velocities. There are more precise approximations. There are endless levels of complexity. So that's the equation-y way thinking about this. The equations very clearly show that energy and momentum are related, and that an object that has energy also has momentum, even if it has no mass. But maybe you're looking for something deeper, something more intuitive. You think that perhaps mass is somehow special. Well, let me disappoint you there too. To first approximation, modern physics has proven that mass is an illusion. There is no mass. Now, you are made of mass, which is true of anything that is made of atoms. The mass of objects made of atoms is found in the atoms' protons and neutrons. The electrons pretty much don't matter. But protons and neutrons are made of smaller objects, which have very little mass, nearly none. So where does the mass of protons and neutrons come from? Those objects are orbiting around each other at crazy fast speeds. You can think of protons and neutrons as tiny subatomic tornadoes, vortices of motion and energy. And that's all they are. If you look at them, there is nearly no mass in the way that we intuitively think about mass. Mass is just energy. Then moving mass is just moving energy. And of course, a photon is moving energy. So when you get right down to it, a moving photon or a moving proton are not so different. Both are nothing more than moving energy. So if a moving proton has momentum, so does a moving photon. And that's really all there is to it. On the other hand, I predict that this whole topic has made you think very differently about mass and energy and how they really aren't all that different. The more you learn about the subatomic world, the more you learn that it's some crazy stuff down there. Well, the first message is that photons certainly do carry momentum. I think the most important message is to always remember that equations only apply in certain situations, and if you try to use them incorrectly, you're going to get confused. The Higgs boson walks into a Catholic church with a troubled look. After indecisively looking at the confessional, he seems to gather his courage and enters where a priest is waiting. The priest says, "Higgs, me lad, what seems to be bothering you?" Higgs boson takes a deep breath and says, "Father Flanagan, I'm thinking of leaving the church." And the priest replies, "Me son, you can't do that." Higgs boson says, but Father, I'm having a real crisis of faith. I have to leave." To which Father Flanagan replies, "No, Higgs, me boy, you don't understand. You can't leave the church. Without you, how can we have Mass?" Okay, you may have heard that one. Now, before I go on, I'd like to apologize to any Catholics who might be offended. But even more, and this is important, I'd really like to apologize to anyone who actually knows what an authentic Irish brogue sounds like. This story illustrates very nicely a common idea, which is that the origin of all mass, including the mass that keeps us firmly on the ground, stems from the Higgs boson. There's just one problem. It isn't true. Now, I don't mean that we physicists have been lying to you. The statement that the Higgs boson gives mass to fundamental subatomic particles and that it is a crucial discovery in our quest to understand the rules that govern our universe is an entirely true one. It's just that the particle's impact is probably different than you've imagined. In fact, the origin of the kind of mass that makes up you and me is from something else. and the real source is actually pretty mind-blowing. So you guys know that you are made of atoms, and if you add up all the mass of the atoms inside you, you'll find that they equal your mass. There's no controversy there, and we can conclude that atoms are the origins of mass. But the story goes deeper than that. We know that atoms are composed of protons and neutrons at their center and electrons that swoop around at great distances, kind of like electron planets orbiting the nuclear sun. Purists will bring up the idea that quantum mechanics and electron clouds, but the fact is, for our purposes, the planetary model of the atom is good enough. Given that the atom has three components, it's probably true that one or more of them is the true source of mass. As it happens, protons and neutrons have about the same amount of mass, so for our purposes, we can treat them as the same thing and simply call them nucleons, which identifies them as particles in the nucleus of the atom. In contrast, the electrons are relatively light. Each electron has only about 0.05% of the mass of the nucleons. So in our search for the origins of mass, we can ignore the electrons. To all intents and purposes, they don't matter. So, can we conclude that your mass comes from nucleons? Well, actually, yes, we can. However, we also know that nucleons are made of even smaller particles called quarks. In fact, each nucleon contains 3 quarks. And here's the good thing. To the best of our knowledge, there is nothing inside quarks. That's the end of the line. So it stands to reason that the ultimate origin of your mass is the quarks, and since there are 3 quarks in each nucleon, each quark carries about 1/3 of the nucleon's mass, and that's the final word. However, there's only one problem. When we measure the mass of the quarks and add them up, we find that they actually make up only about 1 or 2% of the nucleon's mass. So where is the other 98%? To understand that, we need to have an idea about what a proton would look like if you had a magic magnifying glass and could study it. What you'd see is the 3 quarks furiously orbiting around each other in a sphere with a radius of a quadrillionth of a meter. That's 10 to the minus 15th meters for us scientific types. Further, these quarks aren't just lollygagging about. They are moving at nearly the speed of light, almost 300,000 kilometers per second. That's 186,000 miles per second, or almost fast enough to orbit the Earth 8 times in a single second. Objects moving that fast have a lot of kinetic energy, which is the energy of motion. In addition, if something is moving that fast in such a tiny volume, there has to be some crazy big forces holding the nucleon together. Therefore, huge forces have to exist in the nucleon, and whenever you have huge forces, you have a lot of binding energy, or what scientists call potential energy. So this is the first important point. Quarks inside nucleons have a very small mass, but a huge amount of kinetic and potential energy. The second important point involves this guy here. In 1905, Albert Einstein worked out his famous equation, which we now write as E equals mc squared, where E stands for energy, m stands for mass, and c for the speed of light. Basically, this equation says that energy and mass are identical. That's what the equal sign means. And now we can pull it all together. It turns out that your mass isn't what you think. The idea that we're made up of some kind of stuff is wrong. Instead, your mass comes from countless little balls of energy spread throughout your body. Weird, huh? So that brings us back to the Higgs field and the Higgs boson. How does that fit in? Well, the Higgs field does give mass to the quarks themselves and the electrons that we've neglected. In short, the Higgs field is only responsible for about 2% of your mass. So does that mean that the Higgs field is unimportant? No, not at all. If it didn't exist, electrons would have no mass. And if electrons didn't have any mass, then atoms wouldn't exist. And then we wouldn't exist and be here to wonder about it. So it matters a lot. Luckily, the Higgs field does exist, so I'm still here. However, when it comes to the origin of the kind of mass that makes up you and me, there's a different cause. Your mass comes mostly from a single source, the energy stored inside nucleons. In fact, to very good approximation, there is no mass in the way that we usually think about it. There is only the kinetic and potential energy of the quarks orbiting in nucleons, like a swarm of hypercaffeinated bees.